Hi, Joe Cerrone, and welcome to CAD 230 Introduction to Solidworks and our weekly Zoom video meeting. I've released Module 9 as well as Module 8. We were getting a little bit backed up, and Module 8 has been released for the last couple of weeks, but I didn't review it. And so I'm going to talk a little bit about it today. And we're also going to start going into assembly modeling, which is Module 9. And that's really one of the things that SolidWorks does very well, is creating assemblies and simulating motion. So as we look at Module 8 covers threads and threading, and SolidWorks released a thread tool about 3 or 4 years ago. And they show you how to model these parts two different ways. One way is to use a helix and then to sweep a triangle about that helix to cut threads. So if we were to take a look at that, let me just go bring this onto the screen and let's maximize this. Here's an example of the part that we would draw. And if we were to take the Wayback Bar and bring it up, we can kind of see how this part was created. It's created from this profile sketch. If I hit the space bar, I can then go to a normal view or perpendicular. And you can see we have the sketch geometry, it's fully defined. And then once we have this sketch created, we revolve it. And then we use this threading tool. And the thread is kind of grouped, in my opinion, with the features for thread for Hole Wizard. And so here you have the thread tool. And if we look at this thread tool, it's great. It really does the job that it's supposed to do. Let's see if I can edit this. So as we look at this thread, what we do is we select this edge here where the thread would start. And it's really kind of like cutting a thread on a lathe, where you can go in here and you can set up the conditions for that thread. And so we can set up these conditions for the thread. We say that we want to use an inch die. You have the choice of either inch die or inch tap. A die goes around the exterior of the part, like a cylinder, whereas a tap goes into a hole, like this part, an interior cut. And so this is an inch die, and it's a 1.25 die. And we'll take that and we'll put 12 threads per inch, which is a natural standard. Sometimes we need to offset the thread pitch so that it doesn't go too far. You can see that there's a relief here, and we really could offset it because it doesn't really start right on this. And so by using the offset and then offsetting it the other way, we can get that thread so that it starts outside of the cylinder profile. And so we could just bump this up a little bit. Let's just say 0.1. And you want to make sure that the thread lands in this area here. And then if we green check mark this, it goes through and it cuts that thread. And what's nice about using the thread tool is that you can prototype your parts with it. So the thread tool is great. If we go through, we mirror the part, and then we thread the other end of it. And so that's the best part of this chapter. If we look at the other exercises in this chapter, with modeling threads, they go through the old school technique, which is, we can do this on any CAD system. And the old school technique is to draw a helix and then to take that helix once we have it drawn. And here's what they do. They model the nut and then they create this sweep profile. And really what it is it's a bit, a cutting bit like we would use on a lathe. It would be an insert. We use these 60-degree inserts on lathe cutting machines in the shop all the time. And so the geometry is created and the thread depth is created. And so once we have that information, we pierce the helix and then we revolve it, or we sweep cut it rather, into the part. And that's essentially what modeling threads does, is that it takes these thread standards and it applies them. So creating these internal and external threads, my recommendation is to use the thread tool. I think they use the helix throughout a couple of the examples, and I think they just didn't want to update the textbook. They probably had it already written, and so they just did it once. And so you can see they do this thread basically tool, and then they sweep it. So threading is the new component or the learning objective. Everything else we're pretty comfortable with from what I've seen in this chapter. So let's talk about assemblies. If we come back here to the home page and then we look at the assemblies. Now, before I go, lab 8A, 8B, 8C are due. And if it's actually due today, but if you need more time, I'll push that back. I'll accept these next week because we're kind of getting back on track, and I want to make sure that we have enough time to get through all of the material. So module 9 covers assemblies, and there's an assembly pretest located in quizzes and exams, and it's important that you take this. And the reason that I have you taking this is that I have this assessment committee that goes through the courses, and they want to learn, they want to measure our learning objectives. And so the assembly pretest is right here. If I take a look at it, it basically talks about or asks you questions about assembly drawing. The first component should be fixed to the origin. And if you don't know, that's fine. You don't have to look it up. In fact, with pretests, the way they work is that they measure any knowledge that you may have before you read about the content. So you should take the pretest before you go through the content, because then we give you a post-test and then we see if the post-test reflects learning. So the symbol F next to the file name means after the first component is inserted into the assembly, it's still free to be moved or reorientated. And as we go through, just take the pretest. You don't have to do well on it. And then I will have that information for my assessment committee. It says 50 points down here, but it's, and I think I will give you the 50 points, but it's not important to, actually I can't, as I talk about it, because it is a pretest, and if you don't do well on it, you get 25 points, you might say, hey. So this will not be scored. Back to the main web page. So there is a pretest. I give you a little blurb about that. And then as we go into these assemblies and assembly modeling, this is really what's great about Solidworks, because you have the ability to create these assemblies and then work with what's called mates. And mates are what constrain the degrees of freedom in a SolidWorks model. So if we take a look at some of the assemblies, and so here's this one right here. And what we have is these different mates with these concentric mates. If you hover over a mate, it will show you where that's at. You can also right mouse click on them and suppress them, meaning you can turn them off so that you can work with the part if it's not using the correct motion that you're working for. And it has to have some motion. So if you take away all the degrees of freedom, it won't move. And so oftentimes we will troubleshoot these different mates, but most of them are all these concentric mates of a sphere and a ball. And so that we can then go and move this assembly to be able to simulate motion within these parts. And then as we go through and we get better with creating assemblies, we can do other assemblies. And so we have a secondary assembly here of this chain link assembly, and we can go through and we can move these different components however we have them set with our mates. And it will do some things that maybe kind of are impossible, like being able to loop around itself and go through itself. And that's because this is our first mate assignment. And so, yeah, it has sort of that ghostly quality of being able to walk through walls, but we can remove more degrees or apply more degrees of freedom as we go through and work with these different mates. And so I'll include this PowerPoint in the content section of, I believe it's module 9, which goes through and shows you how these different mates work. And so as we work with these different mates, what we do is we take an assembly drawing and we combine all of the different parts. And when we create these assemblies, we'll have all of our different parts. The first one will be fixed, and then the other ones will insert. And as we insert them, we'll put them together. And Sebastian's done a great job of creating videos for that. And so we bring in these different components and then we apply these different mates like parallel, distance, limit, width, hinge, gears, cams, coincidence, perpendicular. It does everything. It's probably one of the big things that, if we go back in time and look at the way cars and other things were manufactured before parametric modeling, they were a lot simpler. And with parametric modeling, we can simulate all the movement of these different machines and mechanical devices. So, you put yourself in the machinist position, or, the person who is going to be working with these parts. And then as we go through, we can go and create these assemblies, and we can extract bills of materials, we can make parts lists. It's a very automated process. And so as we go through, we'll start off with an assembly document, and then that document has the standards like ANSI attached to it. There's two different methods. We're going to be using the bottom-up method, which is simpler than the top-down. Top-down is kind of when you're taking a part and designing it as you're creating these little spin-off parts. And that's how I used to do things when I was a senior design engineer for ITW. I'd make these packaging machines and you'd bring in some of the components, but then you'd have to design things like maybe a sheet metal cover for a flywheel so that somebody wouldn't hurt themselves. And what you would do is you would create the drawing within the assembly and then export it out. That would be a top-down or in-context type of modeling, and it's more complicated. Whereas bottom-up, let's say you have a machine that you've been working on for a long time and you just want to make it bigger and you have all the components. And so you can model those parts and then just put it together and see that everything fits. So you can do some combination methods for those. And as you go through and you insert these different components, we then will be able to create these different assembly drawings. And so this is some information on how to do that. And as we go through, the other thing that I wanted to point out was, how do you turn in a drawing that's been created with an assembly? Well, the way that we're going to do that is we're going to use this pack and go option. And by using pack and go and packing and going to a zip file is the best way, because you can zip them and then put them into the Dropbox. And then I can unzip them and the links stay there. Versus if you put all the individual parts with the assembly into the Dropbox or the assignment folder, the links aren't maintained because it paths where the parts were located. And since I'm opening them on my computer and not the computer they were created on, the path links break. So use pack and go to create the assemblies. Other than that, that's about it for today's Zoom meeting. I'm going to come back here to the main splash page. If we look at the drawings, it's pretty ambitious. We've got Lab 9A, Lab 9B, and Lab 9C. C's pretty robust. You don't have to go through and draw all of these parts. You can download them. You will need this T-joint for the first one, unless you want to model it yourself. You can just take mine and download that. And the parts for the gate assembly are located in the Lab 9 area. And so if I go to contents, and then I come down here to module 9, right here. Here's the links to all of the components. And so here's the gate assembly. You can download it as a zip file and then uncompress it and use those files. All right, that's our Zoom meeting for today. If you have any questions, you can instant message me. I'll open things up for questions and stop the recording.